the section that really isn't big enough to be a section, but they made it its own section. So I will try to expand this video and make it longer by using lots of extra words. But the reality of it is I could explain the whole thing here in about 30 seconds. But I figured this was a great chance to practice some differentiation. So that's what we're going to do. This video is mostly going to be practicing some nasty differentiation. That's it. It should be super fun. Yay! So, what is a higher order derivative? Well, you may have noticed that when we introduced f prime of x, we call it the first derivative. And maybe some of you thought, if that's the first derivative, is there a second derivative? Is there a third derivative? And the answer is yes. You can keep differentiating functions until one, you get to 0 and there's nothing more you could do. It just stays 0 forever. Or until you get bored or your lifespan is over. So, it's certainly a lot of fun for a Saturday night, I'll tell you that. So, but again, I thought, what a great opportunity to write out a lecture and make a video about some of the terminology, some of the symbology that we use. So let's talk about it. I've got a lot of words. You can read them. They're great words. I wrote them all myself. Yeah, it's pretty cool. Literacy, definitely one of my favorite parts of school. Y prime, so the first derivative of y is equal to f prime of x. That's the first derivative of f. That can also be written as dy over dx, which can also be written as d f of x over dx. This is really not as common. What people do tend to write is more like this, where you write d dx as if it were like an operator. It's going to take the derivative of f of x. So this is a much more common form, at least as far as I've seen, but the book is really sure about this one. So I'm going to give that to you to see there too. The one thing that people assume about math that isn't necessarily true is that there is great agreement on all these things. And really there's style. And but the world is very big and people are doing math all over it. And so there are different syntaxes, there are different I can't think of the word. Different accents. You can tell someone's been doing math in another place when you see the way they write things down. So I'm sticking with the stuff that's in the book, and this covers pretty much most of the ways I've seen this written. There's some fancy ways to write it too, but I don't know that it'll come up that much for you. Then f with two of these, and we don't really have this this symbol on the keyboard. It's not really an apostrophe. It's slightly different, but we use an apostrophe because that's what we've got. But two of them means it's the second derivative. So you take a derivative and then you take a derivative again. So it's the second time you've taken the derivative. And there are a couple ways to write it. There are a few more ways. So we've got y with two of those apostrophes, which really should be just more like wedge-shaped. Then notice this, y with two in parentheses. Now this is very important. If you just write, so right here, I'm going to say this is not just y squared. If you see y squared, it's squaring y, so it's y times y. Notice that we've got y with two in parentheses. That specifically means it's a derivative, second derivative. What is the benefit here? Well, if you're going to take the 17th derivative, no one wants to have to count when you go 1, 2, 3, 4, 5, all those hash marks, all those apostrophes, and have to count them up. So when you get to about the fourth or fifth derivative, you start writing it with that number. You can also write it with the function notation like that. And then you can also go to the other way of writing things. Now notice that there's something peculiar here. Down in the denominator, you've got dx, the quantity squared, but up top you have d squared y. And the reason this is, believe it or not, is it's important. And I don't think I'm going to express it very well, but imagine this. And imagine that we use this twice. We would have two d's, two dx's, but only one f of x, right? So this one, dx of dx of f of x. So that would be the easy explanation for what's going on there. So it's a little bit weird. A lot of people look at that and go, whoa, it's going to be hard to remember. And the answer is, okay, just use this. This notation is fine for most of the things you're going to be working with. And then again, we can use this really kind of this version, which I'm vaguely unsettled by, but again, I've learned all the math that I've learned in California, so I have not seen a lot of the wider world of math, so I'm just gonna have to say, you know, it's unfamiliar to me, but I'm sure they did their research. Okay, so what does this actually mean that now that I've just talked for 6 minutes about something that I said I could explain in 30 seconds? Seriously, you should get your money back at this point. I made promises that I did not keep. So let's talk about this. And of course, I have done the terrible thing to you. I've written out those little apostrophe guys and you have to count. So there are 3 of them. So this is the third derivative of g of x. And so the first thing I'm going to do is I'm going to write out g of x, but I'm going to write it slightly differently. Sure, it's x cubed, but then it's minus x to the negative first power. So I'm going to rewrite it, and then I'm going to start differentiating. The first derivative, okay, the 3 comes down. I get 3x squared because we reduce the exponent by 1. Now I've got minus, the negative 1 comes down, and then I subtract 1 there. So the whole thing then becomes 3x squared plus x to the negative 2, which is 3x squared plus 1 over x squared. The thing that I always keep in mind is positive exponents get better, right? They get reduced by 1. Negative exponents get worse. We went from x to the negative 1 to x to the negative 2. Now this is the first derivative. Let's do it again. Woohoo! Second derivative. Now, how do I take the second derivative? I take the derivative of this guy. So in other words, that's a terrible d. Sorry about that. So I've got 3x squared plus x to the negative 2. I take the derivative of that first derivative. This is g prime of x. Hopefully this is making sense. So it's just successive differentiations. Okay, the derivative of this becomes, the 2 comes down, so I get 6x to the first power plus a negative 2x, and then I subtract 1. So this becomes 6x minus 2x to the negative third, which would also be written as 6x minus 2 over x cubed. See how the exponent is getting worse in the second term, but better, smaller in the first term. Okay, third derivative. Woohoo! So we're going to take the derivative of the second derivative, which was 6x minus 2x to the negative third. So this is second derivative of x right there. When I differentiate 6x, I get just 6. And then I get negative 2, and then the negative 3 comes down, and I subtract 1. And I get 6 plus 6, because the negative 2 times the negative 3 gives me 6. Pardon me. And I subtract 1, and I get x to the negative fourth. And again, I think we've discussed this in previous videos, but even though this is technically correct, if the problem is given and the exponent is written positive and in the denominator, your answer should match that. Sometimes people hold you to it, sometimes they don't. There we go. That is the third derivative. So it just means to take derivatives over and over again. Woohoo! Okay, Let's try some more. Are you ready? This can't be so bad. Huh. What in the world are you going to do for the rest of the video? Dun dun dun! This is nasty because I'm going to be invoking the chain rule, because I just made the chain rule video and I thought, I bet they could use some more practice. And I know, I hear you all saying, no, we don't need more practice. And I'm saying, yeah, let's do some more practice. So, first thing I'm going to do is I'm going to rewrite f of x. I know I'm taking, this is the second derivative. Woohoo. So we're going to take the second derivative. So I'm going to write the first derivative in a form that will work for the chain rule. And in fact, it's not even the chain rule. I don't have the power rule written down. I should have the power rule written down somewhere. Okay. Well, I don't have it on a clever card. So I'm trying to remember how I wrote it, but I'll just write it in. I'll write it in line. Okay, so sorry about that. A moment of confusion. You know, when you don't have your props in the right place backstage. This is why you don't move other people's props. F of x is, and I've got 4x minus 5 on the inside, and remember the square root or radical is going to be a 1/2 exponent. And basically the rule of the taking the derivative with a power there. I'm going to take the first derivative, and I'm writing it with primes rather than writing this. You can always make it look pretty at the end. I find this notation to be easier to write. Sorry, Leibniz. I know you had such great plans for all of this, and now we're like, eh. Okay, so first thing that happens is, remember, the 1/2 comes down just like a regular old differentiating a power. So this stays the same. Remember, the inside stays the same. And then you take the original exponent and subtract 1. Then you multiply the derivative of the 4x minus 5. So this is going to be the derivative of 4x minus 5. 1/2 times 4x minus 5. 1/2 minus 1 is negative 1/2. That's nobody's favorite thing. Or maybe it is. I don't want to yuck your yum. And then over here, I'm going to multiply by the derivative of this, which the derivative of 4x is 4, and the derivative of 5 is 0. So all together, I've got 1/2 times 4x minus 5 to the negative 1/2 times 4, which is equal to 4/2 times the quantity 4x minus 5 to the negative 1/2. And that's equal to 2 times the quantity 4x minus 5 to the negative 1/2. So again, what happens with the chain rule or the power rule? Remember, you take the derivative of the outside with the same inside, and then here, the derivative. Oh, that's exciting. Am I still recording? I am. Pardon me for a second. Apparently someone is trying to make a phone call. Sorry about that. Okay, let's hope. I'm generally not popular enough for anyone to call me, but let's hope that doesn't happen again. So I was saying this is the derivative of the inside. So the inside function is the 4x minus 5. Okay? Now, that's just the first derivative. Yay! So now I have written this all out, and it is, especially if you're going to keep taking derivatives, I definitely recommend trying to clean stuff up. Like this 1/2 and this 4, I could have left it, but it's a lot easier to clean it up and get everything canceled so that this whole thing is a lot less to deal with, because now I have to differentiate again. Yay! So remember what happens. The 2 just hangs out because it's just multiplied. So the 2 gets left there. Then the negative 1/2 comes down. The 4x minus 5 stays the same. And now I've got negative 1/2 the old exponent minus 1, because that's the rule for dealing with exponents. And then I'm going to take the derivative of 4x minus 5. Now we know from above that's just the number 4. So let's see, I've got 2 times 1/2, and then the 4x minus 5. Negative 1/2 minus 1 is negative 3/2. Take a moment there if you need to. Okay. Times, and then, oh my goodness, I see it. I see a mistake. Yay, I caught it before I forgot to catch it. Do you see my mistake? I'm going to finish up this line, the derivative of this. Some of you are screaming at the screen. Some people are like, what? There's a mistake? There's absolutely a mistake. So let's talk about what came down. The negative 1/2 came down. That's a negative number right there. That should be negative. Sorry about that. I know some of you are like, I can't believe you did that. And I'll say, yeah, sorry about that. Now, what have I got? I'm going to bring the 4 over here. So I've got 8 times negative 1/2 times 4x minus 5 to the negative 3/2. Okay, so 8 times negative 1/2 is a negative 4 times the quantity 4x minus 5 to the negative 3/2. So just very quickly, I want to point something out. Whenever you go into negative exponent territory, if you take successive derivatives, it starts to flip-flop because this one is negative. The first derivative is positive, then this one's negative. Now, if you think this negative exponent is going to come down and multiply, that's going to make the whole thing positive. So it's going to create a flip-flop. Each successive derivative will either be positive or negative because of that. Now, this is technically the correct answer, but again, I'm going to try to write it in the correct format. So it asked for d squared y over dx squared, which is exactly equal to this. Same meaning, different symbolism. I should say, it does refer to slightly different things. So like they're nicknames, but they refer to basically the same person. And then let's see, I think I've got a negative 4 on top, and then a 4x minus 5 to the 3/2 in the denominator. Now, this is usually acceptable, and I realize there's a little squiggle there that looks like something that is not a squiggle, so let me cover that up. There we go. Usually this is sufficient. I don't know why I can't draw 3's and 2's right now. But you could also write it as negative 4 all over radical 4x minus 5 cubed. So you could split the 3/2 up into the 2 parts. This is really an or situation, and it just depends on what you're looking for in that particular problem. But that's our second derivative. Yay! You guys made it. Hopefully got some good practice. I don't know if you can hear it. I've got a gull outside who's very excited about taking derivatives and the chain rule. They do. It's a fun fact. A lot of shorebirds really are into calculus. It's absolutely true. So like if you're out on the beach eating a big sandwich doing calculus, all the seagulls will come in to try to learn calculus from you. True story, true story. Okay, number 3. Again, I'm spreading this concept out. I decided to do this application because just because it was a problem that I assigned in the homework, because I wanted to check to see if you could decipher it, and then I realized that some people were getting frustrated, so I thought I would just show you how to do it. So we've got a revenue function. Hopefully at this point you're so used to revenue functions, right? We've got revenue of x. So our revenue is 300x minus 0.05x squared. And I wanted to talk about this. Find the instantaneous rate of change of the marginal revenue. Okay, so this is the marginal revenue. And we've been flirting with this. We will discuss marginal analysis a little bit more in the next section in 9.9. But basically, the marginal revenue is already the derivative. It's the first derivative. And then if I say, what is the rate of change? So how fast is the derivative changing? Not how fast is the revenue changing, but how fast is the slope changing? That's what I'm talking about here. So this says take the derivative. Take the derivative, I'm running out of room, take the derivative of this. So that is why it's a second derivative. Does that kind of make sense? Take the derivative of this guy. So we've got the marginal revenue, that's the first derivative, which would be, so this is the marginal revenue. And I think this is universal, but I'm not sure. So those of you who've done more business classes, I tended to stay on the economic side of things, so I don't know. I think this is pretty universal for marginal revenue. Is the first derivative, so that's 300x becomes 300. And then this one minus 0.05 stays there, the 2 comes down, and we subtract 1, right? That's the exponent rule. So we get 300. Now, interestingly, it stays minus, but this is 0.05 times 2, so it's 0.1, right? I believe so. Now, fun fact, the thing I'm worst at is this kind of multiplication. So let me just, it seems simple, but I want to double check it so I don't leave you with mistakes that'll make you want to throw things at the screen. 2 minus 1 is x to the first power. So this is our marginal revenue. This is the function that gives us the slope of the revenue, how the revenue is changing. And then to take the second derivative, well, this becomes 0, right? If we take another derivative, and this one, if it's just negative 0.1 times x to the first, then it becomes just 0.1. The x disappears. And so our second derivative is negative 0.1. So now what does that tell us? Well, it tells us a few things. That the slope is decreasing at a constant rate. It also tells us something. This is bonus learning right now. So the second derivative is the concavity of the function. So what does that mean? That means whether the function is concave down or concave up. And the really cool thing about this is they match smiles. So if your second derivative is positive, greater than 0, then it's a smiling face. If your second derivative is less than 0, then it's a frowning face. That's it. Woohoo. Okay, so I spread out this 30-second concept into 23 minutes and 44 seconds. So woohoo. Congratulations on making it through. And good luck on the homework, and make sure you go out and get some vitamin D and get some exercise, get lots of rest. Be gentle with yourself. Calculus is not easy the first time. I ended up taking it 3 times to get it really solid. So, you know, if the first time through you're feeling like, I don't even know what's going on, just be gentle with yourself. Know that you're awesome. And I really appreciate that you've made it through all these videos I've been making. And, you know, remember